You have felt this. A tap slams shut and the whole house of pipes bangs, once, hard. That bang is a pressure wave, and it can hit hard enough to split steel. Today we simulate it from scratch, and then we do something dangerous. We trap a gas pocket in the pipe and watch what it does to the spike. Here is the pressure at the valve, straight from the solver we will build. Steady flow at 50 meters of head. Then the valve slams. And the head does this. 148 meters of overpressure, arriving in under half a millisecond. That is roughly 15 atmospheres, slammed onto the pipe wall by nothing but a closing valve. No pump, no explosion. Just inertia meeting the wall. Why does closing a valve create a wave at all? Two ingredients, both of which we usually ignore. Ingredient 1, inertia. A column of water moving at 1 meter per second has real momentum. When the valve shuts, that column does not stop politely. It piles into the closed valve like traffic hitting a wall. Ingredient 2, elasticity. If water were perfectly rigid and the pipe were infinitely stiff, the whole column would stop instantly and the pressure would be infinite. It is not, because water compresses a little and the pipe wall stretches a little. That give and take sets a finite speed at which the stopping signal travels back up the pipe, the wave speed A, about 1200 meters per second in water-filled steel. Parts 1 and 2 transported one scalar at a fixed velocity. Water hammer is a genuine step up, pressure and velocity now evolve together as a coupled pair. The first equation is continuity. If the velocity changes along the pipe, the head must change in time, scaled by the wave speed squared over gravity. The second is momentum. A head gradient accelerates the flow, and friction, the same Darcy term from part 1, drains it. Two coupled partial differential equations. H and V, hand in hand. The crucial word for this pair is hyperbolic. Hyperbolic systems carry information as waves, traveling at a finite speed, here plus or minus a. That mathematical fact is the bang. And it hands us the perfect tool to solve it. Solving two coupled PDES sounds hard. But hyperbolic systems have a superpower. Along special lines in space and time, the PDES collapse into simple ordinary differential equations. Those lines are the characteristics. Draw space across and time up. From every point, two lines leave, a forward wave, the C plus characteristic in teal, and a backward wave, C minus in coral, each with slope 1 over a. To find the state at a new point P, we ride the C plus line up from the left and the C minus line up from the right. Along each line the PDE becomes one algebraic equation. Two lines meeting at P give two equations and two unknowns, the head and velocity there. Add them, you get the head. Subtract them, you get the velocity. No matrix, no iteration, just add and subtract, marching up through time. That is the entire method. There is one price. The characteristics must land exactly on grid points, so the wave speed pins the time step, a times delta t must equal delta x. The grid is not a choice laid over the physics. The grid is the wave. Before we trust a single number the code prints, we need something to check it against. For instant valve closure, there is an exact law, from Joukowsky, 1898. The head rise equals the wave speed, times the velocity you destroyed, divided by gravity. It is almost insultingly simple, and it falls straight out of momentum. You stopped a column moving at v0, and the wave speed assets how violently. Faster flow, or a stiffer pipe, means a bigger bang. Our numbers, 1200 times 1.207 over 9.81. 147.6 meters. And the solver's very first peak? The same, to 2 decimal places. 0% error. When your code reproduces a 120-year-old hand calculation exactly, you can start to trust what it says next. 7 steps, and the core is famous for a reason. The method of characteristics is mostly addition and subtraction. Step 1. The physics constants. Wave speed 1200. The impedance B is just A over G. The friction resistance R is the Darcy factor folded into the reach length. Note there is no pipe area here, this is the velocity head form, and getting that convention right is the difference between a clean run and a solver that overflows to infinity. Ask me how I know. Step 2, the grid, and the constraint that makes MOC so elegant. The time step is not free. A times delta t must equal delta x, so the wave crosses exactly 1 reach per step. 200 reaches, and the clock follows. Step 3, the valve. A single function, tau of t, ramping the opening from 1 to 0. Set the closing time to 0 and it slams instantly. Set it to several wave periods and it eases shut. This one function controls the entire severity of the hammer. Step 4, the heart of the method, and it is just addition. Gather the C plus invariant from the upstream neighbor, the C minus from downstream. The new head is their average. The new velocity is their difference over 2b. No linear system. No iteration. Every interior node, every step. Step 5, the boundaries, where the physics enters. The reservoir holds head constant and lets the backward characteristic set the velocity. The valve combines the forward characteristic with the orifice law, and that coupling is what launches the wave when tau drops. Step 6, the twist. This episode was voted in 4. Replace the valve boundary with a trapped gas pocket. The gas obeys a polytropic law, pressure times volume to the K is constant, so as liquid compresses the pocket pushes back. It is a spring made of air, bolted to the end of the pipe. Step 7, march, log the head at the valve, and validate against Joukowsky. If that assertion ever fails, the physics is wrong and the script refuses to pretend otherwise. Verify, or it did not happen. Now watch the wave itself move. This is the head all along the pipe, the valve on the right, the reservoir on the left, every frame straight from the solver. The valve slams, and a front of high pressure is born at the right wall. It sweeps left toward the reservoir at 1200 meters per second, flips there, and races back. Watch it reflect end to end, and watch friction slowly bleed the peaks down each time it passes. This ringing, up and down every 33 milliseconds, is the pipe hammering itself. Now the multiphase twist you voted for. Trap a pocket of gas at the valve, 2% of the pipe's volume, and slam it again. Gas is hundreds of times more compressible than water. Intuition says it should soak up the blow like an airbag. Let us test the intuition. The intuition is half right and half dangerously wrong. In gold, the pocket. The first spike does collapse, from 148 meters down to 29. A five-fold cushion. The airbag works. But here is the warning every pipeline engineer learns the hard way. A gas pocket is a spring, and springs have a resonant frequency. Cushion the spike at the wrong pocket size, or hit it with repeated valve operations near that frequency, and the pocket stops absorbing energy and starts storing and returning it, amplifying later peaks above the rigid case. Trapped gas is not a safety device. It is a gamble. The reliable fix is boring and in teal. Close the valve slowly. 8 wave periods turns a 148-meter bang into 5. So, we started from inertia and elasticity, built the hyperbolic head velocity system, solved it by adding and subtracting characteristics, checked it dead on against a century-old law, watched the wave hammer the pipe end to end, and discovered that a trapped gas pocket is a cushion you cannot fully trust. Part 4, your call in the pin pole, column separation, where the pressure drops so low the water tears apart into vapor and then slams back together, or surge tank design, the engineered cure. The MOC solver, the gas pocket model, and the full derivation PDF are in the flow from scratch pack below. If you would rather understand the bang than fear it, subscribe. See you in Part 4.